So let f be the function defined by the square root of the absolute value of x. So I see a lot of good work of rewriting this function as a piecewise. But how does writing it as a piecewise help you? It doesn't help you unless you actually differentiate, right? The whole point. So then this group here, instead of differentiating, they said, well, let's just look at the graph, right? And the graph's a much easier way to do this problem. If you have decent graph knowledge, now this graph technically, right, should be, there we go, right? Okay. So there we go. But it doesn't matter because the general shape is fine, right? And that's really what tells you. So they did it with the graph, which is how I would have done it. But these guys did it with a piecewise derivative, which is beautiful. And what happens is if you ever do have to differentiate piecewise, never put an equals under your function, or under your x value, under your like greater than less than sign, because most of the time, not all the time, but often when you differentiate piecewise, this number ends up being an undefined spot for your derivative, usually because what happens is the slope on one side of that number is not the same as the slope on the other side of that number. Now, in this case, it's undefined both places. Like this is undefined at 2, this is undefined at 2. The derivative is undefined at 2. Like there's no way around it. Your derivative is undefined. It's super undefined at 2. Not only because it's a sharp turn, but it approaches the slope of the tangent actually approaches infinity. It actually approaches a vertical tangent from both sides. So even though, so you got like a double, like this is like super mega undifferentiable because your slope, this function actually does this kind of a thing. So your tangent from the right approaches vertical, the tangent from the left approaches vertical, and you end up not only with a vertical tangent, but you also have a sharp turn because from the left you are approaching a negative infinity slope, and from the right you're approaching a positive infinity slope. So you're like opposite slopes and vertical tangent. You're super non-differentiable there. Yes.
Is there like a hole, or would there be an
There's a dot. Because the actual, this is the function's defined at 2. 2 minus 2 is 0.
Oh.
You have a dot there.
Oh, but it's not different.
But it's not differentiable. So this answer would be, the answer is continuous but not differentiable. The answer was A. So the function's totally continuous. The limit as x approaches 2 from the left is 0. The limit as x approaches 2 from the right is 0. Therefore, the limit as x approaches 2 is 0. F of 2 is 0. So the limit equals the function. They're both defined. This function's continuous. So it's continuous, but it's not differentiable. And I actually drew like kind of what you guys did on the board here. So, and to me, this is, again, looks like a verb function, right? So you end up with that sharp turn. All right, so let's get into today. Today we're doing 4-4b. 4-4b. If you like to give your notes a name, you would call this L'Hopital's rule day 2, or L'Hopital's rule continued. 4-4b, second day of L'Hopital's rule. Do you actually know the movie Breakin' and
No.
Breakin' 2?
I just know.
Electric Boogaloo?
Yeah,
Do you know that that's from a movie called Breakin' in the 80s?
I know it's from a movie.
Oh.
Electric Boogaloo just became a meme.
Really? Oh. In the 80s there was a movie called Breakin', and then Breakin' 2 was called Breakin' 2 Electric Boogaloo. So it was terrible. They were both horrible movies. Yeah. They were both about breakdancing. A lot of breakdancing. That was big in the 80s. Okay. So we are going to, oh shoot, I lost my window shade. Hang on. I had a shade on this and I lost it.
I resaved this last period at the end of the period because I added a screen to we did a little handwritten recap screen at the end. And so when I saved it, I lost my shade. All right. Okay, so take 20 seconds in your groups and discuss what infinity minus infinity equals. Go.
No one knows. Infinity's not a number, it's a constant. Yeah, but infinity's not a number.
If it's a constant.
It's not, it's a concept.
Yeah.
It's unfathomable. No mere mortal can subtract infinity from infinity.
Okay, I love these. I'm going to pull it in.
From 0.
All right. How many? Did any group say the answer was 0? One?
I say
Some
it's
half
I
groups?
say it's
Half
0.
groups say it's 0. Okay. Did any group say the answer was infinity? Okay, a few other half groups. All right, we have some division amongst the ranks. All right. Does anyone say that it can't be determined? Oh, we have some of you voted 3 times. Okay. All right. Good. So I have a couple of questions for you. So the set of natural numbers. Natural numbers are your counting numbers. They start with 1. 1, 2, 3, 4, and so on, right? If I take the whole set of natural numbers and I subtract the whole set of natural numbers, what am I left with? 0, right? In that case, infinity minus infinity would equal 0. So everyone who said 0 would technically be correct for that instance, right? What if I took the whole set of natural numbers and subtracted only the evens? Are there infinitely many even natural numbers?
Yes.
So what am I left with? Infinity. Infinity minus infinity, in that case, is infinity, right? So what if I took the set of real numbers and subtracted the set of natural numbers? Real numbers are all of your numbers that, apart from imaginary, right? Real numbers include decimals and fractions and non-terminating decimals and all the weird numbers in the world, irrational, right? Square root of 5 is a real number. Every real number. What if I took the set of real numbers and subtracted the set of natural numbers? What would I get?
Wait, I have a question first. Are negative numbers real numbers?
Yes, negative numbers are real numbers.
So if you have all the negative numbers and negative decimals, and then all the positive numbers and positive decimals, wouldn't they just cancel each other out?
Okay, so very good question. I'm not talking about subtracting the numbers from each other. I'm talking about subtracting the number of numbers that there are.
Oh.
So what we call the cardinality of the set, which is how many elements are in the set, minus how many elements are in the set. That's a very good distinction. Thank you. So, yes, if I took the number of elements in the set of real numbers and subtracted the number of elements in the set of natural numbers, what would I be left with? Would I be left with 0? Would I be left with infinity? Infinity for sure. What if I just took the real numbers between 0 and 0.1 and subtracted the entire set of natural numbers? What would I be left with?
Infinity.
Still infinity. Because there's more numbers between 0 and 0.1 than there are in the entire set of natural numbers. Okay. So, because there's so many reals, right? There's so many. All right. So where does this come from? So the first it's Mathematician Monday, and we're doing it right at the beginning this week. So, Mathematician Monday, we're going to talk about George Cantor. So we have a couple different pictures of George Cantor, young and old. He was Russian, but he moved to Germany when he was young, born in 1845. So this is not that long ago. I mean, I know it feels long ago to you guys, but it's not
like in the history of the world, this is relatively not that long ago, right? Okay, so he is the founder of all what we call set theory. Set theory, if you decide to explore higher mathematics, set theory is something you will explore. It's kind of interesting. It gets to be a little bit tough, but you'll grow your brain. It's really fun. So it's tough, but it's fun. All right. He was the first to introduce the concept of different sizes of infinity, which is what I heard Jennifer talking about when she was trying to talk to her group, right? Oh, and Faith, both of you are talking about sizes of infinity. Thank you. All right, good. So infinity has different sizes. How can something that doesn't even exist have different sizes, right? Okay, so he labeled all sets as either finite. Finite means you can count the elements. This set has 7 elements, right? You can count the elements. There's a starting element, there's an ending element, there's a finite number of elements in between, right? That is a finite set. Or infinite denumerable or infinite non-denumerable. Denumerable, in essence, kind of means countable. So a denumerable set is a set that can be mapped to the set of natural numbers. What does mapping mean? Mapping means, can you write a function to get you from one to the other? So if I were to, maybe I should do it on the screen. I'll do it on the screen since it's, so if I were to write the set of the natural numbers, right? And then we did evens. So 2, 4, 6, ... Is there a what's called one-to-one mapping, right? Where it's like some way to just say this goes to this, this goes to this, this goes to this. Each number is assigned a number in the new set, right? If there's a nice one-to-one mapping from this to this or vice versa, then this set is called denumerable. So a nice way to think of denumerable, it's not the definition, but it might help your brain to think of it, is if I name an element in a denumerable set, you should be able to name the next element in the set. So if I say 5, you can say 6. But if I'm in the set of real numbers and I say 5, yeah, there's no specific number, right? So there's no next number. So when you're in a non-denumerable set, you really can't name the next element. Now, believe it or not, rational numbers are denumerable, and ordered pairs are denumerable. I remember when I was first learning ordered pairs as being a denumerable set, I'm like, how can you name the next ordered pair? I couldn't figure out, like, how do you know which one is next? And the way that Cantor did it was he did this little spiral thing, and he said, well, start at 0, 0. Like if I put dots at all we're just talking about ordered pairs of natural numbers. So what he did was he started here and he just did a little spiral around. You can map the ordered pairs to the rational numbers, because remember the rational numbers are just your fractions, right? So if you map all the ordered pairs to just fractions, just do like an x over a y or a y over an x. Now you've mapped all your ordered pairs onto your fractions, and if you can map your fractions onto your numbers, then you've got a denumerable set. So anyway, that being said, then you've got your real numbers, which are definitely non-denumerable. All right, his work on ordinal and cardinal numbers and the cardinality of sets is phenomenal. So what's really fun, so I talk about clicking on these links. But he was constantly laughed at, totally dismissed by his colleagues. Back then, nobody bought it. And so everyone pretty much just told him he was a fraud. And so he ended up suffering from constant depression throughout his life. Now, if you look up his Wikipedia and you start clicking on stuff, it's really kind of fun. You'll get into this deep world of set cardinality. And so, because what makes it really fun is if you take the number of elements like in natural numbers, right? So you got a nice infinity there. Now if I said, all right, well, how many subsets are in the set of natural numbers? So subsets, so like the set of the number 1 and the set of the numbers 1 and 2, 1, 2, and 3, 1, 2, 3, and 4. What about, 2 and 3, 2 and 4, 2, 3, and 4, right? 2, 6, and 13, right? All of those are subsets of the set of natural numbers. You get into a higher degree of infinity when you start counting subsets. Then if you start counting subsets of subsets, right? So you end up with these like levels of degrees of infinity, and it's really kind of fun. When you start counting the subsets, it gets like all crazy. Anyway, all right. So a deep study of set theory makes your brain hurt. It really does. But then, of course, your brain grows. Every time your brain hurts, it's growing, right? I love the diagonal theory he came up with later on in life, mostly because I can understand it. I don't, in all honesty, I haven't looked at it in several years. I don't remember the diagonal theory, but we could look it up. I remember thinking, oh, that's not that hard. Like I get that. So, but I don't remember what it is in all honesty. I'd have to look it up again to tell you. So anyway, but that's George Cantor. So George Cantor devoted a large part of his life studying the concept of infinity, which we are using today with our l'hôpital. All right, so today we're going to take what we learned on Friday and expand it to more types of limits. So the L'Hopital's rule didn't change. L'Hopital just says if you have a limit that's 0 over 0 or infinity over infinity, you can take the derivative of the top, derivative of the bottom, and have an equivalent limit. All right. Well, now we're going to apply this to other types of limits to see if we can convert them and still use L'Hopital to figure them out. So the first type we're going to talk about are indeterminate products. Indeterminate, I don't know if you remember, indeterminate just means can't be determined the way that it's being presented. So if you have a limit and you plug in the number and you get 0 over 0, that is an indeterminate limit, meaning it is a limit that based on its present state cannot be determined. You have to do something to it. So indeterminate just means can't be determined the way it is. So all day we're doing indeterminate limits. All right. So the first one we're going to talk about is if you have 0 times infinity. Does 0 times infinity equal 0? Or does 0 times infinity equal infinity? Well, it all depends, because we're not talking literally about 0 times infinity. We're talking about the limit as something approaches 0 times the limit as something approaches infinity. So if you take the limit as something that's super small times the limit as something that's super big, which one wins? Does the super small thing suck this thing down and make it equal 0? Does the super big thing pull this thing up and make it equal infinity? Or do they kind of cancel each other out and you end up with some number in between? So every case is different. That's why we kind of do these on a case-by-case basis. So our first type of limit that we're going to talk about, so there's 3 types we're going to do today. So you don't have to write all this down. But the first type we're going to talk about is 0 times infinity. 0 times infinity. All right. Are you ready? Heck yeah. Here we go. So first example of the day. Happy Monday. We have the limit as x approaches 0 from the right of x times the natural log of x. Before we start in this limit, I have a question for you guys. Why did I have this be the limit as x approaches 0 from the right? Why didn't I just do the limit as x approaches 0?
Because it doesn't.
Hey, you guys are good, and it's Monday. Because the natural log doesn't even exist to the left of 0 or at 0. It only exists to the right of 0, right? So because the natural log of x only exists for positive values of x, you can't do the limit as x approaches 0 because then it'd just be a big EN. So you have to do the limit as x approaches 0 from the right. What is the limit as x approaches 0 from the right of x? 0. What is the limit as x approaches 0 from the right of natural log x? Negative infinity. This is a 0 times an infinity case. All right. So I'm going to just write this down. So this is a 0 times infinity type, which makes sense because that's what we've been talking about. All right. Whenever you have 0 times infinity, you have to put something to the bottom. Something has to go to the bottom. If you put something to the bottom, that'll force it to become either 0 over 0 or infinity over infinity, depending on which thing you put to the bottom. And it really doesn't matter. You'll get the right answer either way. Personally, in this problem, the easier thing for me to drop to the bottom would be the x. So how do we just move something to the bottom? Well, you can't just put something on the bottom because we'd be changing the question. But we could if I did that. So I can't just move the x to the bottom, but I can move the reciprocal of x to the bottom. Now I've turned my multiplication into a division question. What is the limit as x approaches 0 of natural log of x? Negative infinity. What is the limit as x approaches 0 of 1 over x?
Infinity.
It is positive infinity. And it's such a good thing. I'm so glad that you guys remembered all your graphs from the last couple of years, right? 1 over x. So as x approaches 0 from the right of 1 over x, we're pointing up to infinity. All right. So we have an infinity over infinity. Does it matter that they're different signs?
No.
No, it doesn't. So now we can L'Hopital. But before we actually L'Hopital, what do we have to do first? We have to justify it. So we write the limit as x approaches 0 from the right of ln x equals negative infinity. Limit x approaches 0 from the right of 1 over x equals infinity. Therefore, L'Hopital applies. All right, we've justified our L'Hopital. When we actually apply the L'Hopital, we just do the derivative of the top and the derivative of the bottom. So everyone take a second. Do the derivative of the top and the derivative of the bottom. What's the derivative of ln x? 1 over x. What's the derivative of 1 over x? Negative 1 over x squared. This is x to the negative first, so derivative is negative x to the negative second, or negative 1 over x squared. Before you start trying to evaluate your limit, always clean it up, right? Always clean this up. So this is equal to the limit as x approaches 0 from the right of what?
Negative x.
Just negative x, right? Could you flip this, put it up there? Get negative x squared over x. Negative x. So what's our limit? 0. So 0 times infinity. Whenever you have 0 times infinity, you're going to have to rewrite as a division problem. And then you look at the top. All right? Type number 2. This is the type from our second warm-up Mathematician Monday problem, which was infinity minus infinity. It's a minus sign. It kind of looks like an equals, but it's a minus. So our second type is infinity minus infinity, which we have already very much established we don't know the answer to. Depends on the situation. All right, so type 2 is indeterminate form infinity minus infinity. You don't have to write all this other stuff. All right, let's do an infinity minus infinity question. So now we're going to do the limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. Ooh. What does ln x approach? What's the natural log of 1? 0, right? So you're thinking, all right, well, 1 over 0, that's just DNE, right? Okay. The problem is you got a DNE and a DNE, and which really, these are infinities. How does 1 over 0 give you infinity? Well, when you are, this is ln x, right? If I'm approaching 1 from the right of 1 over this, well, think about your, just numerically. If I'm approaching from the right, so my numbers are all positive. So let's say this is 1. 1 over 1 is 1. 1 over a half is 2. 1 over a third is 3. 1 over a fourth is 4. 1 over a tenth is 10. 1 over 1 100th is 100. 1 over 1 1,000th is 1,000, right? So the closer you get to 0, the closer your 1 over graph is actually going up to infinity. Same thing over here. This guy's going to start it here. It's actually be an open circle. I'll go down. Yes?
So are we saying that 1 over 0 is infinity?
We are saying the limit as x approaches 0 from the right of 1 over x is infinity, which is what this is.
And that's the case for the last one.
Yes, it is. For both of them. Yeah. All right. So, and I will tell you, if you're just trying to like think, because you don't, like obviously on your actual work, you don't have to draw any graphs or anything. And so when you are thinking these through, if your brain wants to think 1 over 0 is infinity and 1 over infinity is 0, that's fine. You know, just for thinking about it, because that'll work for all these limits. So when you get a 1 over 0, think infinity, and when you get a 1 over infinity, think 0. All right. So what we end up then, let me write the type. So this is an infinity minus infinity type. All right, what do we do when we have infinity minus infinity? Well, lucky for you, these are both fractions, so we just combine the fractions. Take a second and combine those fractions. LCD. All right. If we're okay with LCDs, plug in a 1 on top. What do you get? 0. Plug in a 1 on the bottom. What do you get? 0 over 0 means we can lhopitals. But before we lhopitals, we have to justify. X approaches 1 from the right. X minus 1 minus ln x equals 0, which equals limit x approaches 1 from the right of ln x times x minus 1. Therefore, l'hopital applies. All right, go ahead and l'hopital it. What rule are you going to have to use for the bottom? Product rule. Good. All right, check your derivatives, see if we match. What should we do before we continue on with this? I would multiply the whole top and the whole bottom, not by 1 over x, but by x, right? Get rid of all those complex fractions. So I would multiply the whole top and the whole bottom by x and just clean it up.
Would it not be x ln x for the bottom?
Oh, thank you. X ln x. Good multiplying there, Ryan. All right. Okay. Plug a 1 into the top. What do you get? 0. Plug a 1 into the bottom. What do you get? 0. Which means we can L'Hopital again, but first we've got to justify it again. Okay, so everyone take a second and re-justify your new L'Hopital. All right, what's the derivative of the top? 1. The derivative of the bottom is 1 plus, what rule are we going to have to use? Product rule again. So now can you find your limit? So the answer to infinity minus infinity is 1/2. No. Yeah, sorry.
Wait, it's just this infinity? It's like not universal?
Correct.
Oh, can you explain that? Like this infinity?
No. I can't. I can't explain why this infinity minus the infinity is 1/2. It just works out that way. Yep. Anisha, can you explain it?
Does that mean there's 1/2 more number than?
Like if you subtract all the elements of one from all the elements of the other, you end up with a net change of 1/2.
Wait, do you think this is real or like made up? Like, do you think math is invented or like?
It's a whole different topic.
That's a little deep for a Monday morning.
That's really deep. I like to think of it as both. I like to think of math as both an art and a science, right? Because it's everywhere in the world. Like there's everything in the world has math in it. Like if you look at anything, you can apply math to whatever you're looking at. But it's not like cavemen went into a cave and found a pile of 3s, right? I mean, we created the number system. So in that sense, I think it's created. It's an art. However, every single thing, once we've agreed upon what we created, every single thing since then has been proven. So once you agree on these concepts, everything after that, nothing is made up. Everything is proven. So because of that, I think it's a science. So So math is actually considered a science. Like if you go to college, math is going to be one of, and it's a natural science. It's considered part of the Department of Natural Science for most colleges. So I think of it more as a science than an art, but there is art to it because in the beginning we made it up, right? All right. Yes, Ishan, what's up?
You said infinity is like the number of numbers inside a set, right?
Well, that's one type of infinity, is the cardinality of a set, the number of numbers inside a set.
Alright, so let's say you have an infinity times infinity. How can you have like half infinity?
So in this case, the infinity isn't the number of numbers in a set. In this case, the infinity is literally what number is this function approaching, right? So we're not talking about a set, we're talking about an actual numeric value. So if, as x approaches 1 from the right, the closer that your value of x is, if you plug in 0.0001, 0.000001, or 1.000, you get it, 1.0000001, right? 1 and 50 zeros in a 1, 1 and 100 zeros in a 1. And you take whatever value you get from this minus whatever value you get from this, you're going to end up with a half.
So it's like a really, really big number that you don't want to write down.
Correct. But if they're a half apart.
Oh.
They're both going to approach super big numbers, and they're going to be roughly 1/2 apart. Yeah. All right. Good. Like thinking for a Monday morning. First period didn't like to have any of this discussion. So, all right. Okay. This is review. I want this on your whiteboards. This is not what we're doing now. This is actually from chapter 3. See if you can figure out what's the derivative of x to the 2x plus 3. Group eventually figured out you had to do log differentiation for this. When you do a log of both sides, you can take that exponent and put it in front. So then you differentiate both sides. So the derivative of ln y, 1 over y dy dx. What rule does the derivative of the right side require? Product rule. Okay. So the derivative of 2x plus 3 is 2 times ln x plus, I'm going to write my pet peeve here, 2x plus 3 times 1 over x. Okay. Now, wait, there's more. There's more. Okay? So, I will look at students and I'll say, okay, you're missing something that's really, really important, and if you don't put it, all of your math is really essentially wrong, right? And so I'll say, what are you missing? And then they'll say parentheses, and I'll say, okay, put your parentheses, and they'll do this, right? Okay, which is what you've got on your board. So, sorry, not to throw you under the bus there, but I'm throwing you under the bus. So, because you don't need parentheses around a monomial, what's the point, right? Why do you need the parentheses? It's to show that this entire expression, it's the binomial that needs the parentheses. The 1 for x doesn't need parentheses. The 2x plus 3 needs the parentheses, right? So don't just put parentheses in random places. You got to put it around your groups, right? Around your groups. Okay. All right. So, sorry, I didn't mean to, make you feel bad. Oh, same thing here. Holy cow. What is going on, you guys? You have to be better with your parentheses. So if you're missing parentheses on your test, I'm taking off. I'm not counting. All right? Because you changed the whole meaning.
Yes.
Okay. All right. So dy dx equals, so you get 2 ln x plus 2x plus 3 over x times y, which is x to the 2x plus 3. All right. So, everyone, the main thing here, apart from me harping on you, was just to know to take the log of both sides, right? All right. So whenever you have an x to the x, you have to take the log of both sides. Same thing holds when you have a limit of something with x's to something with x's. So whenever you see an x to the x with a limit, you're also going to take the log of both sides. So when you have a 0 to the 0 or an infinity to the 0 or a 0 to the infinity or a 1 to the infinity, again, you're going to be taking the log of both sides. Because, like, we don't know. 0 to the 0 is 0 to the 0, 0 is 0 to the 0, 1, right? Well, how do we know, right? Well, when we're doing a limit, it could go either way, or it could go even to different numbers. So that's why we're going to use logs in order to evaluate these limits when you have something to a power. So people are writing, so that's fine.
Always straight.
No, it's just some people like to write everything, and so or take a picture. You really don't need a picture, but you know.
4.5. Are we going to do exams for all three of these?
No,
Not all three?
nope.
This is freshman 4.5 notes supposed to be up for like smartboard notes because I saw them online.
So 4-5 is the day that I'm out.
Okay.
So I pre-recorded your lesson in advance, and I did it last week, and I went ahead and put it on Schoology just so it was there. Yes, so you haven't learned it yet. That's okay. So that's what you're going to be doing with your sub on Wednesday is watching the video and then working through the homework together, and maybe finishing up a quiz also. All right. Okay, so, oh my goodness, doesn't this one look like fun?
Oh my gosh.
Okay.
Yes.
So, let's do the limit as x approaches 0 from the right of 1 plus the sine of 4x, all raised to the cotangent of x. Let's figure out what type this is, right? Okay, what is the sine of 0?
One.
What is the sine of 0, AP Calculus students?
0.
It's 0.
Oh, I thought you were asking about like the
No.
sign, like negative or positive.
Oh.
I was like,
0 doesn't have a sign. Okay, no, the sine of 0 is 0. So what we end up with in here is a 1. Now, the cotangent of 0, just in case you might not remember cotangent of 0, so tangent looks like x cubed. I always remember tangent is looking like x cubed. It passes through the origin, looks like x cubed. Cotangent is tangent flipped over and shifted. So cotangent, you end up with this like upside down x cubed that's been shifted over like that, and it just repeats in both directions forever. So if I ask you the cotangent as x approaches 0 from the right, what do you get? Positive infinity. So this is a 1 to the infinity type. 1 to the infinity type. Okay, so what we need to do is take a natural log of both sides. But we don't even have two sides. We just have one side. So the first thing that we have to do is set this equal to something. I personally always just call it y. You can call it any letter you want as long as it's not x. So whatever you want to call it, you will always see me call it y.
That's just a really long.
Now that we have it set equal to something, now we can take a log of both sides. But before you do the log of the left is easy, right? Ln y, done. All right, piece of cake. All right, oops, that's a y. All right, the log of the right, this requires a theorem. We learned this theorem, and we wrote down the theorem, and we talked about it for about 40 seconds, and then we have never looked at it ever again. It is not the squeeze theorem. The theorem that I'm talking about is actually the limit of a composition of functions. So you did. It is back in chapter 2 when we were doing our limit properties. We listed in properties of limits. So, oh my gosh, you really don't have to look it up. It's okay. So anyway, so what it says is if you have the limit of f of g of x, that's ascent and f and g are continuous, then that's f of the limit of g of x. Like you can take the outer function outside of the limit and you have an equivalent limit. We're actually going to do that in reverse and take the outer function and put it in. So when we have the cotangent of the limit of 1 plus sine 4x, that's the same as the limit of the cotangent of the ln of 1 plus sine 4x. So we're kind of using that composition theorem in reverse. I know can you just accept it?
Sure.
Okay.
Yeah.
All right. So, do you want me to prove it? Okay. All right. So anyway, all that being said, the reason I'm saying that is that when you take the natural log of the right-hand side, you can keep the limit on the outside. So you don't have like an ln of a limit of. You just keep the limit to the far left and then just do all your other stuff. So now we have the cotangent of x times the ln of 1 plus sine 4x. I kind of skipped a step there. I'm sorry. I put the exponent in front right away. All right. So now let's see what we've got here. So we've already established that the limit as x approaches 0 cotangent x is infinity. And here, what is the natural log of 1? 0. So now we have an infinity times 0. So this is an infinity times 0 type. So we've gone from a 1 to the infinity to an infinity times 0. What do we do when we have an infinity times 0?
Drop 1.
Something's got to go to the bottom. So what would be easier to put to the bottom? The cotangent. And do not write, when you put cotangent to the bottom, please do not write it as 1 over, how do I say this? 1 over cotangent. What is 1 over cotangent the same as? Just tangent.
Yeah.
When you are multiplying by cotangent, it's the same as dividing by tangent. And it's a lot easier to do the derivative of tangent than the derivative of 1 over cotangent. Okay. All right, take a second. Oh, first we got to justify. So now, the limit of the top, we end up with ln 1, which is 0. What is the tangent of 0?
In the front? No, 0.
0. You've got to learn our trig. Tangent of 0 is 0. So because we have a 0 over 0, now we can L'Hopital, but before we L'Hopital, we have to justify it. So we have to write the limit as x approaches 0 from the right of ln of 1 plus sine 4x equals 0. I don't have space to do a three-way string, so I'm just going to write them separate. Tan x equals 0. L'Hopital applies. Do you think if next year, if I suggest to the honors pre-cal teachers to not allow you to use any notes or reference sheets on any of your trig tests, that you would learn your trig better?
We don't.
Then how do you guys not know your trigs?
We do sheet tests every day for like 3 weeks. If you give me it in the right format, then I can
So what you're saying, if I hear you right, is we need to start doing a summer assignment.
No.
Helping people remember their trig.
Why don't we just do speed tests now? Like start the day off like a 10-minute speed test. Yeah. Why can't we just do speed tests? Whatever. Let's just do some speed tests.
All right. You guys have to L'Hopital this thing. I am not helping you. Take a minute, do the derivative of the top, do the derivative of the bottom.
Yeah, do I do L on Y?
No, remember, L'Hopital is not, you're not differentiating both sides. You're just rewriting an equivalent limit, right? We're not differentiating this side. We're just saying, hey, what's an equivalent limit to this? We're going to apply L'Hopital, do derivative of the top, derivative of the bottom. Yeah, do not differentiate both sides.
It's secant. Yeah, it's secant. Yeah, I'm going to have to read those. Oh, it's 4 cosine for x. Or cosine for x.
Yes.
X over 1 plus sine of
How do we do with our derivative?
Good.
Good. What formula? Like the derivative of tangent? Yes. Yes. So the derivative of natural log, quite aptly, the derivative of natural log is u prime over u, right? D guts over guts. Guts go on the bottom, derivative of the guts go on top. Derivative of tangent is secant squared. That you just have to know. All right. So if you, by the way, if you ever were in a pinch and you really needed a derivative of tangent and you couldn't remember it, if you know tangent is sine over cosine, you could just do quotient rule on sine over cosine, right? So you could. Anyway, all right. So now I got to clean this up. There's a lot of ways to clean it up, but there's one way that works really nice, right? So dividing by secant squared is the same as multiplying by cosine squared, right? So we can actually rewrite, notice guys, just so you know, when I'm working these problems, I rewrite my left side every single time. Don't just string the equals because you'll forget, because we got to do something with this when we're done. So I have the limit as x approaches 0 from the right of 4 cosine cubed 4x.
Wait, where did you get that?
Because dividing by secant squared is the same as multiplying by cosine squared.
Secant x, not secant.
But it's 4x, just secant.
Oh, you are so right. Oh, nobody even pointed that out to me on the first period. I wasn't even paying attention to the argument. Thank you so much. There you go. You guys get a personal star for the day. All right. Okay, thank you. All right, so now we've got that. So let's actually see if we can evaluate the limit. So if I plug a 0, what's the cosine of 0? 1, right? So what's the top of this whole thing? 4. All right, so we know it's not going to be another L'Hopital. Okay, let's plug into the bottom. What's the sine of 0? 0. So what does the whole bottom equal? 1. So what we get is ln equals 4 over 1. Now our limit isn't ln our limit is actually just y. So we still have to solve this for y. How do we solve ln equals 4 for y? We don't take, we already have an ln. We don't want to do more ln's.
E both sides.
We e both sides. And you know what that's called? Exponentiate. We exponentiate both sides. So we get y equals e to the 4th.
Dude, that's crazy.
Yeah, and that's our limit. So if I ask you the limit as x approaches 0 from the right of 1 plus sine of 4x raised to the cotangent x, the answer is e to the 4th. All right, isn't that crazy? All right, we're almost done. I have 2 more for you to try on your own. You can talk to each other though. So work with your groups. This is for your fun. Okay. So for the first one, I rewrote it. So when you plug in infinity, e to the negative infinity is actually approaching 0. So you have a 0 times an infinity. So whenever you have a 0 times an infinity, something's got to go to the bottom. The natural thing to go to the bottom looking at this is the e, because e to the negative x is just 1 over e to the x, right? So you just drop the e to the x to the bottom, and then you justify your L'Hopital, both approach infinity, L'Hopital applies. So when you apply it, you end up with the limit of 1 over a whole bunch of stuff. this whole bottom is approaching infinity. It's 2 times infinity times infinity. It's like super infinity. So when you have 1 divided by infinity, the limit approaches 0. Whenever you have a constant divided by infinity, you're going to 0. Any questions on the first one? The first one was a nice, happy one.
Yes.
Okay, let's do the second one. So for the second one, we have a 0 to the 0 situation, which means we're going to have to take a natural log of both sides, right? So I set it equal to y. Take the ln of both sides. When you take the ln of both sides, remember, keep your limit on the outside of your log. So you end up with x ln sine x here. All right, so now if we plug in a 0, this is 0. But if we plug in a 0 here, you get the natural log of 0. So the natural log as x approaches 0 from the right is actually negative infinity. So this is actually a 0 times an infinity. So something, again, has got to go to the bottom. I personally would put the x to the bottom. I think it's easier than doing 1 over the natural log of sine x. So anyway, so I rewrote it like this. Now you got to justify your L'Hopital, because when you plug in, now you get an infinity over an infinity. You actually technically get a negative infinity over an infinity. All right, so now we L'Hopital this thing. The derivative of the top, so I'm going to just kind of, because I know that I don't write this out. Limit x approaches 0 from the right. All right, the derivative of the top, so sine goes on the bottom. What's the derivative of sine? Cosine goes on the top. The derivative of the bottom, x to the negative first, is negative x to the negative second, or negative 1 over x squared. So, I think I actually have this right. All right, so, yeah. All right, so when you clean it up, you get negative x squared cotangent x. So again, you end up with a 0 and an infinity. So you have to, again, put something on the bottom, and you get to L'Hopital again, right? So I put the cotangent on the bottom, called it tangent, and then had negative x squared over tan x, which both approach 0, therefore L'Hopital applies. Derivative of the top, negative 2x. Derivative of the bottom, secant squared x, but I just moved it up and called it cosine squared. All right, so the limit as x approaches 0 of negative 2 times x is 0 times 1 is still 0, so you get a nice limit of 0. Are we done? Is that the answer to our limits? No, what do I have to do? I got to exponentiate both sides, so y actually equals e to the 0, which is 1, therefore our limit is 1.
Not the same answer, but
Yeah.
I don't know if you did it right.
No, we skipped the second L'Hopital.
Yeah.
How did you get an answer of 1 from the first, from this?
Magic.
Magic?
If you plug it, it's always going to be 0 times whatever cotangent is.
Which approaches infinity.
Ah.
Because we're approaching
God.
x at 0 from the right. So you have 0 times infinity.
So we got
Yeah,
lucky.
we just skipped the
You got lucky.
L'Hopital.
Yeah. All right. Good. Okay, so we did a little first period recap. So 0 times infinity, rewrite it as division. Infinity minus infinity, you're going to combine the fractions. And anything with an exponent, whenever you have some kind of a funky exponent situation, you're going to take the natural log. You have now completed L'Hopital.